Hello everyone. So welcome to the continuation of the previous episode, the tutorial that we are following. So I guess we have reached a point where we created the box, that's the region, which is the material is actually the air. So yeah, that we have assigned already. So what we need to do further is, uh, well, there are few things that you need to know. As I've already mentioned, uh, we did something related to 3D components and modeling. And well, in model section, there is a lot of stuff that will go on parallelly. For now, we have moved on from here to the boundary section. So what happens in the boundaries is that we actually have to associate, uh, mm, I don't know how to put this forward, but let's imagine we are about to excite the coil. Now, to excite the coil, we need to energize the coil. So to do that, let's say basically we do that with the help of current, right? Let's say 5 ampere current input and exit from another point. So one will be the input side, one will be the exit side. But to do that, though we have terminal here, as you can see, well, yeah. And furthermore, if I select the box and cross this is hide selection. So if I do that, the box disappears and it becomes a lot easier, yeah, like this. So we can operate around the coil. So we can see that the terminals are there present, and if I press F in the keyboard to select the face, I can select the terminal like this. So this is the face of the terminal, right? So here are two terminals. One is in the below side, down side, in the zeroth position, and one is here. But even those terminals are available, if I excite the current in this terminal and decide one as input and one as output, even after that, I will not be able to actually simulate. Why that happens is because of the boundaries condition. Because this coil is not attached to the boundary line of the region that we created just now. And the region is nothing but the air, the box. So when we see that coil is actually surrounded by this box, right? And that coil is somewhere in the middle portion of the um, region, and it is not touching the region, so the boundary conditions are not satisfied. So if we want to excite the coils to simulate the results, we need to fulfill this criteria to touch the boundaries of the region. So the end boundaries will be this surface somewhere here, let's say this front surface. So this surface must be touched by the terminals. So how we do that? So for that we need to draw some extra structures leading from the coil to the boundary line, and it must perfectly touch and align with any one of the surfaces of the region of this box one, to name it. So I guess you have understood what I'm trying to say, and if we do that, then only the boundary condition will be met and we will have a check mark here, and then we'll move on with excitation. So yeah, so let's fulfill that boundary condition. So how to fulfill that boundary condition is we actually draw a lead. So two leads will be drawn, and the two leads will actually lead to the boundaries, and those leads will yeah, to the boundaries from the terminals. So we will connect the terminals with the boundaries with the help of leads, and that lead will be obviously the copper wire. And yeah, basically the lead will then act as the terminals and not the real coil, and we will try to keep those leads very small in diameter so that it doesn't come under the consideration of the coil, just to neglect the effects of it. Well, yeah, that is how we approach. So let's approach the design. So how we do it exactly is, first let's hide the box and then view the isometric perspective, and then we zoom in to see the terminal. And when we see the terminal, so how we do it, um, so yeah, just to give you a slight idea about the axis. The red one is x-axis, the green one is y, and the next one, the blue one, is z. So you can see we the terminals are actually ending and starting at the z-axis. If you can see, this is the first terminal, and the coil is started, and then it ended again at the x-axis. So where the x-axis meets, the terminal actually ends there. So we'll make our leads generating from these terminals towards x-axis. Well, you can draw at to any side of the uh, any face of the box, but it will generally help you, and you will understand it better, and you will learn quick if it's in the direction of the axis in which the coil is touching. So that's x-axis for now. So we will just try to face the surface that is actually perpendicular to the x-axis. So if I bring the box in again, you will understand what I'm saying, because the x-axis is facing this surface right here, this surface of the box. If I select S and I click the surface, sorry, the face, and I click the surface, so this is selected. So this is the surface, yeah, this is the surface that we want to connect the leads with, leads that are connected to the terminal of the coils. So I guess you have understood now clearly so what we are trying to achieve, and this surface is perpendicular to x-axis, so x-axis will be the direction where we will throw our leads. You will become more clear when we do it. So let's go on, dive into it. Fit all, and it comes here. I will, with the help of the scroll button in the mouse, I will press it and slightly move it. So it becomes a lot easier when you use your mouse, and I will zoom it. Yeah. Now after this, this is the terminal, and I will select the draw line option from here. Yeah, the draw line is selected. You can see it's selected, and then I will bring it near the terminal, and you will feel that it attracts towards the center. So it automatically represents a circle in the center, and then it automatically goes to the center as if like it goes there effortlessly. So you will exactly know the center of it without any difficulty. So when you move the cursor to the center, just click it once there and then drag it towards this side, just roughly. You do not need to have the exact measurements right now because we can edit it later. So just drag it towards a direction, most probably in this direction, which I'm doing right now, and then click it again and click it here, and then again drag it in this perpendicular direction. Well, it might not be exactly perpendicular if you look at it, but if you see it perpendicular, just do it. Do not think about it. Now, when you do the next line, when you draw the next line, bring it somewhere here and double click it. So you have to double click and it will be drawn. So it might be very confusing in the first attempt. So you might be very confusing because look, when you see it, there's no line at all. So, but please do not be confused because we can now actually move the line to where we want it. So let's go to the polyline. The line is created. It's called polyline, and there is create line, create line. There are two boxes for two parameter settings for two lines because we created two lines. And we'll double click this parameter, and now when you double click it, you can see that line is particularly highlighted here. Now this is what we want. We have already decided the center of it, so we want actually move it from that axis, and you must again remember the axis, or you can take the axis perspective from here. X is this side, Y is this side, and Z is this side. And looking at that, the X is fixed. Please do not move the X, because if you move the X, this center will move from its place. So, and we do not want to do that. Point 1 actually represents this point. So we want to move that, and this particular value is very important because that's where we want to align our complete line. Whereas we can see that this line is not completely aligned to this point. This point is not aligned with this point. That is where the line is not actually parallel to it, right? So we'll copy the X parameter here, the X coordinates, and we'll paste it here. And when we apply, you can see both of these are actually aligned to the same X values, but you can see it's not what we want, right? That's because of other Y and Z values happening there. Now Y value is 0 here, and you can see the y value is this direction. That means it will come forward in this direction, and that we do not want for this point at least, but we'll particularly want for this point, because it must change in the y value for this point but no change in y values for this point, because it must be attached to the solid. So for this point y value 0, that's very valid, and it must be like that. And let's come to z-axis. Z-axis is again a certain default value there, because we actually selected the center. So if we move the z value, it will move the point again in the vertical direction. So that we do not want. Again, we want this z value to be exactly similar with the second point too. So in the same way we copied the x parameter, we'll copy the z parameter too, and we will paste it right here. Let's see. So it says 3 point. Okay, the comma is missing here. Oh, I missed something. I actually deleted the, well, use 0. Okay, I guess it will work now. Let's apply and see. Well, I see that the polyline has gone missing, and that's because I actually messed up with the y value of the second point. So let's do OK there and repeat the process. That happens because when you do this, and look, we learn from errors and mistakes, and probably I'm making mistake and you are learning better, because I can improve this. I can work around with few things like that, because I've been using this for a long time. But again, mistakes happen, and you are lucky that you are about to see what happened. You actually saw what happened, and you're about to see the solution again. So you will draw it again. You will take the line, you will put it somewhere here. Yeah, now it is detecting the center. That circle denotes the center. This is the exact center. So I will draw this line this side somewhere, right? Okay, and then again draw this side. Double click, it has generated the line. Go there, see it, copy the whole thing. Okay, not copy the whole thing, copy the x-axis, copy it, paste it. Okay, it's 20, and we'll make it similar to this 25 and see apply, and we'll see. Well, now I guess it has done the job quite a while now. Yeah, it's good, right? It's working. Now it might seem that there's something wrong with it, because that's because it's large. The y value is very large. That means the extension from point 1 to point 2 is very large. So we'll reduce this to 5, and 5 will be enough. Because remember, the coil actually turns around. So yeah, this is good. So if you want to confirm, you can actually check it, but it is very difficult to check line. So let's not do that. Let's go to the second setting, second parameter setting. Now the point 1 of this setting will be the point 2 of the previous one. So it will be exactly same to that. So it will update it from there. And now what we do is we actually copy it wholly. Like we'll copy it and we'll paste it ditto. And what we'll change is the x value. Remember what I said? We actually extend the lead in the x direction, because now we have process the first line, and the second line will be extended in the x direction. If you remember, that will be our lead, which will be meeting with the surface of the cuboid or the box, or the surface that I selected previously. So if you remember that, we are going in that direction. So, and for now, put it very arbitrarily, and please try to make it very long, because later on we'll crop that thing to the border. So to make it easier and not to calculate things in head, we'll just do it 1000 mm, and 1000 is sufficiently long, so we do not have to worry, because later we can subtract that. We'll do apply and OK. So this line is created for 1000 mm long. Obviously it is going to meet the surface that we have decided to touch it with. And yeah, when I did the wrong line making, So the error actually was thrown here, and it actually describes what exactly is wrong with the design. So it's not a problem. Sometimes you can go with the error that are coming here, and you can actually troubleshoot things. Right? It's very easy. And when you draw the line, actually we are not uh, trying to establish just a line, but a solid figure. So to convert this line into solid figure, what we'll do, we'll select the create line, create polyline. That's the master uh, parameter of the both of the two lines, right? So it will select the both of the lines. Now, here in the cross-section type, we will change the cross-section type to circle because our structure is circular. And when you do that, there will be dialog box that will be indicating the width or diameter of it. So I will just indicate the diameter to be 2 mm for now. So I will hit enter and it will draw the solid line. And now you can confirm because you can see the solid line. So you can confirm that it is actually parallel and it is actually attached to it, right? No error. So that's how you do it. You do fit all and you can see that the lead has extended all the way this long, whereas our coil is this much small and our lead is so long. Now what we'll do is we'll subtract this lead later on to the surface and just attach the surface with the lead. That we'll do later on, but for now we need to drop another lead right here using the same process, exact process. Now the lead in the terminal is in another side, so I will use again the rotate feature by pressing the scroll button in the middle and I will rotate it. That's the easiest way to do. So slowly I will manage. Again I will rotate from this side, again I will rotate from this way and from the sides. Now this view is the perfect view to actually create the line, or maybe slightly more. Okay, now this is good. Again go to line, so hover around. When you hover around, okay, it's look, this is the problem. It's actually showing triangle but not the circle. So until and unless you don't get the circle, it's not the center of it. Uh, and if it's not the center, it might have problems sometimes. So yeah, here's the set. So if it's not centered, try not to do it because when it's not centered, it's catching another vertices from another surface, maybe the surface that is just behind it. So what that creates is it will create an illusion to you. You will feel that it's the center of it, but when you actually draw the solid, it will actually go and get attached to that back part of the surface. So that will be a whole lot of problem because it will throw an error later on. There might be current leakage and so on. So do not do that. So until and unless you get the circular portion like this. When you get this, click extend. So I will just extend arbitrarily, it doesn't matter, and then again extend because I guess this is the x direction, so I will extend this side. So double click, sorry, and when you double click, it actually creates the polyline. So the polyline 2 is created. I will just go there, same process. So it's 0 0. Why it's 0 0? Because the lower terminal is actually created from the 0th position. So it's quite easier. Just copy this and paste it. So before pasting, here is -6. You might have doubts. So I won't erase that, but I will just copy the X point because X point is mandatorily you need to copy that. You can use your mind and you can actually you can search why we did this because it takes some time to get around what we're doing exactly to get the grasp of it. So you will be fine. And then the z-axis is actually changing, whereas our y-axis must be changing and z-axis must not be changing for the first line. Remember, it must be parallel to the xy plane. So we will make that 0. Whereas we must change the y-axis because it must drag from this point. The second point must be away from this point by some y-axis value, and that value is actually 5 mm, I guess. Mm, yeah, but it's not working. Or okay, yeah, I did it wrong because it must be -5. You can see the axis here. It must be -5. I don't know if it's working or not. Let's see if it's all fine. Yeah, I can see from this side that yeah, it's perfectly parallel and it's working quite fine. Well, it's working. So yeah, you can move around like this and you can actually confirm if it's working. So yes, so this we will exactly copy it and paste it, and what we'll do is we'll change the point 2 to 1000 mm because x-axis we are going to change. When you do that, it actually transfers the value from there to there and transforms the line. Okay, I guess it's good. So go to create polyline again on the create polyline section. Go to the cross section type, make it circle, and change the diameter to 2 mm and just click somewhere outside. Now you can see line is created. So it is created. I guess it is perfectly fine. Yeah, it's good. So I confirm it's parallel to, yeah, it's fine. Now go to orient, isometric view, and fit all. So we have drawn, I don't know if you can see, but I can see here. I guess you can see that. I can see in my monitor, yeah, the two leads are here and these two are now acting as a terminal. But the thing is, the idea was to attach all these two terminals to the boundary. And the boundary is nothing but this box. So let's see where the box fits now. So box is here somewhere and our terminals are somewhere here, our terminals are somewhere here, and the box is somewhere back here. So we need to subtract this uh, figure and attach it with this face. So face is very back and the leads are very in the front. So this is a hack and a trick to do this thing very easily. So you do not have to calculate all the things and the lengths and so on and so forth. You do not have to do that. So there's a trick. You just go and enable this box first. Okay, I do this. Now I can see the box. And then what I do is I create another box, another cuboid on this face. So this is the face that we are trying to attach to. Now what we do is we create another face, but when I do this you can see I cannot draw in that direction. So I will press escape, that will escape the part, and I will change the coordinates because it's not xy coordinate. If you see this face, it lies in zy coordinate. So just go there in the section and change to yz coordinate. So when I change, you can see the grid lines have changed and oriented themselves in the zy direction. And now again go to the cuboid and select the vertices like this. Yeah, it will detect itself, and you can confirm that from the bar below. It says 500 minus 500, and that's exactly the size of cuboid. Now click it and then pull it in this direction. Pull it says that it will cover the lead wholly. So your lead must not be outside of this region. So just to make sure, just go to the maximum length and click it somewhere. That's how you do it, right? Now I'm pretty sure that the leads are totally enclosed in this new box. So yeah, that's fine. Now the trick is this box. Now please notice this box. What's the name of this box? I will press O button in the keyboard. That will enable the object. Now yeah, I can select the object. When I click this, it highlights the box 2, right? So I can confirm that by clicking the box 2. Yeah, it selects this one. So the name of this box is box 2. So I need to subtract this box with the lead line that I created. But before I do that, I must ensure that the lead lines are actually the part of the coil. So the coil is actually the air core inductor. So that is selected. Whereas the lead lines are here, they are individually separated. So we do not want this. First, what we want is we will assign two polylines, sorry, not assign, but we will actually unify the polylines with the coil. So first select the coil. It is selected in order. Please remember it's selected in order. So I will select air core inductor first, then press Ctrl and select polyline 1 and then select polyline 2. After doing this in this order, I will go to this section here that says unite those objects and I will do unite. Did I press that? So let's do it again. Okay, yeah, now it's doing. So it will take some time, and actually it will unite these three objects together, and it will put that as in the name of Air Core Inductor. So you can see the material has changed and everything has come inside copper. Inside copper there is Air Core Inductor, and there is a unite method that has binded these two together. So that's what we did. So now property wise, all the leads as well as the coil itself is selected as one unit, and it's a coil. Now after doing that comes the part of the box. So we'll subtract, now again in the similar manner, this is box 2 that needs to be subtracted. And when you do this, actually the leads get cut from the exact surface where we want it to be. So yeah, to enable that, we'll select the Air Core Inductor and then press Ctrl and select box 2 in the same order. Please remember the order have to be exactly in the same manner. Otherwise, if you do the reverse of it, actually the box will get subtracted from the coil, and that will omit the coil, and only a part of box will remain. So that's not what we want. We want to subtract the coil from the box, because there's part of coil inside the box. So, and we will do subtraction here. Yeah, so the blank parts is this and two parts is this. We'll do OK, and the box will get omitted. Yeah, and this is what we want. And here was our lead, and that is there no more. So where is our lead? Our lead is extending up to the face that we want. This was the face, and it is exactly extending up to that. So if you want to see that, just zoom in and you can see this circular portion here. So yeah, because we created that external box, the box 2, from this surface, it has exactly cut the lead exactly at that surface. Now that is what we want to satisfy the boundary condition. This is what we want, right? So this is the let's say this is the current in, and there will be another secondary terminal, right, which we will regard as, yeah, this one here, as current out. So further excitation purpose. So yeah, we have done that. I guess you understood what I did just now. And let's now go to the box and just hide it, and then again come back to the. So now till here what we have done is we have actually completed the boundary condition. So check mark on the boundaries. Now it's a turn of excitation. Yeah. So excitation is very simple. You just decide whether uh, to excite this. These are the terminals. These are the terminals, and we want to excite the coil with a certain amperes of the current, and we have to decide terminal 1 and terminal 2, that is terminal input terminal and output terminal. So let's say the first one, the upper one, is the input terminal for me. And to select the terminal, again press F key, select, right click, assign excitation, and then current. So this will open this dialog. Let's say I in, and then give the value of variable I. I will select I. Well, when you give variable, and I want it to be stranded, so stranded I, and just press enter. This will open a dialog, and here you specify the real value of the. So I will specify 5 ampere, 5 amperes, right? So yeah, it's current, and I will do OK. It's done. It's showing the direction. I will go to the second terminal now. That will be assigned as, sorry, second terminal here, and this will be assigned as output terminal. Assign excitation, current, again I, this will be output terminal, I out. I will press I, and when I press I do not need to mention this. So when I do I, it's already, I have made that variable. So I will do stranded and swap the direction. Please do not forget to swap the direction, because one will be input and another will be output. And when I press OK, it automatically assigns 5 ampere because that variable is created. If you want to check the variable, just click in the Maxwell 3D design here, and you can see I is a variable which is a ampere, which is current value of 5 ampere. Now what we have done is we have actually done the excitation part here. So yeah, fit all, and let's see, I in this and I out in this direction. That's perfect. um, I don't know if I have to end this video here, or let's do one more thing. Now yeah, this has come sequentially. We have done the model, we have done the boundaries, we have done the excitation. Now parameter. So parameter, just right click here, assign, and do matrix. So this is nothing but the excitation that we actually created. So, but we need to take this as a parameter to create a matrix. So we'll select the current. Yeah. You can see the effect here. It is actually creating a matrix. So simulation is all about matrix. It has created a matrix and we have created the parameter. Now comes the point of mesh operation. So mesh is actually the finite element analysis is actually the mesh analysis. So mesh is very small units that is created inside this structure that helps to calculate, um, that has to actually simulate the things around. So there are units of it, there are shape of it, there can be triangular mesh, there can be circular mesh, there can be, so the more coarse it is, the less time it will take, the more fine it is, the more time it will take for simulation. So we will try to set the mesh settings in the coarse and not in fine, just to make sure that the simulation will not take that much long. To just see the initial settings of the mesh, we can right click and see the initial mesh setting here. And if it's in coarse, that's fine. That's what we want. And please keep the mesh method in auto if it is not. That will be a lot easier. But how to create mesh? How to create mesh is what we do is we'll do fit all. Sorry, the box is not here. So first we'll enable the box, view the box, and we'll do fit all. And after the box is selected like this, right click anywhere, it doesn't matter, and assign mesh operation. Mesh operation inside the selection. So when you select the region, you will do inside selection, because you have to do the mesh analysis inside the selection in that space. So because of that, you will do inside selection and you will do length based matrix. So here I will write region res, and the longer the element length is. So this is what finite element means, right? So the longer the length is, the more error will be in the output, or it will actually run faster, but the output will not be that much practical. So try to maintain it somewhere around 50, 80, or 100, depending on how much big is the region. So here I can see it's around 700 mm. The region length is around 700 mm. So I guess 80 mm will be fine, and not less than that or more than that. It's fine. You can give any value. So one of the mesh is created for region, but this is not enough. So you can see the region mesh is created. Now the second mesh will be for the conductor, for the copper, for the coil, right? So we will right click anywhere after selection, and we'll go to mesh operation and we'll do on selection. So for copper, for the coil, we'll do on selection and length list. And we'll write coil. Since the coil is a lot smaller than the region, we'll try to keep it smaller. Let's say 30 mm. Okay, so okay, that's done. So the mesh for the inside is also created. So two meshes are created, coil and res. Now, okay, that's being done. Now is the turn for analysis part. We will go to analysis, right click, and add solution setup. So this will open this window where number of passes is 10. So it is number of passes is nothing but it will repeat the simulation process 10 times. So there will be 10 adaptive passes. So for each adaptive passes, it will check the values, and it's kind of, yeah, iterative thing. And percentage error, I will actually recommend 10, because it makes it whole lot faster. So 10% percentage error of 10 is not that much drastic difference in the original value, so it doesn't matter. So 10 will be good because it saves your time, at least for now. Convergence, yeah, you can actually put number of passes 10 and convergence of passes maybe 1. Yeah, it's okay, but I want to leave it to default. Solver, please enable the alternative solver. That will be good. Yeah, that's it. So that is all. We have actually created analysis. The optometrics part is actually for the sweeping output. So if you want to do some distance sweep or some frequency sweep, that is when the optometrics comes in place. For now, we are only interested in calculating a certain inductance value. So that doesn't need optometrics. You will need optometrics when you want to calculate the coupling between coils. So at that time, you can use optometrics and swipe the distance, and then you will know that at what distance what coupling coefficient between the coils exists. So for those operations, optometrics is required. For now, we are skipping that. Then comes the result part, where we will actually produce a result. When you right click here and create magnetostatic, because the solution type is magnetostatic, we'll go to that portion. Now we are not creating rectangular plot for sure. So what our output will be is we're actually trying to establish the L value, so data table will be enough. We'll select data table, and here you need to make sure that parameter is checked to the matrix one that we created. And the primary sweep doesn't matter that much because inductance value is not affected by all these things. It's actually the physical property, and thus it doesn't matter. And it's by default by the way, you can't change this. It's by default set to I because we have used only one variable here. Now go to the L and then select this one. So it's fine, right? We'll create new report, and that will give us the I. That's a variable, so it doesn't matter that much. What we need is this. So it's showing in nanohenry and this, but it's not calculated because we have not done the analysis yet. So it's time for analysis. The video is going quite long. It doesn't matter. We can finish it today. This is the end of it, right? So yeah, we have done. We have come to the end. The field overlays I will show later on how we create field overlays. So Maxwell design, double click here to see the coil. What we do, we go to simulation now and we validate the design. So it runs, so it check marks everything that we did. So yeah, it says it's fine. We have not done any mistakes, so there's no any leakage for now or nothing like that. So it's time to analyze, and we click on analyze all to calculate the value. Analyze all. Now, before we do that, we need to save the project. So yes, let's save the project. Okay, I'll just save it with that name. So it will take some time to save the project first, and then the analysis will run, and it will take uh, pretty amount of time, not that much, but yeah, it takes some time. So till then, uh, you can do few things, but if your configuration of the laptop is very low, then you might not work in your laptop. Well, I will not recommend to work do multitasking in the laptop. If you are running a simulation like this, you are running an analysis, that will, like, you will be the saddest person on the earth because your laptop will your laptop can crash, and like it freezes like hell. You can't do anything at all. It has, like, this is my experience, and I have gone through better experiences than this. So please, if your laptop has a lower configuration, please do not use your laptop when you run simulation like this, or do not multitask or try to multitask when you run the simulation. Just leave it as it is. Come back, have coffee, do something, watch movies, and then come back. That will be enough. But if a laptop has a decent configuration, more than 8 gigs of RAM, 16 gigs of RAM, very high and latest powerful processors, that will be pretty good. It won't make a problem. So yeah, we can't wait that much. It's already about 40 minutes to the video. So I will just cut the clip from here and show you the final results. So yeah, uh, this is it. After the simulation was run, what we found out that the inductance came out to be 25 microhenry, and it is under the simulation results. So this is how you look at it, right? So if you want to, so once the analysis is run and you want to see other results, You can now go to the table and actually or plot anywhere. It will bring you to the same window, and you can actually generate whatever there is. For example, the magnetic flux. So you do not need to run the simulation again and again. Once the analysis is done, it will show the value immediately. So for everything that is under the result, it's established immediately. So in Weber, this is the value, the magnetic flux. So this is how you do it, right? So this was the basic fundamental thing, how you design a coil. Now, let's assume that you were supposed to design a coil with 60 microhenry self-inductance. So this is not it, right? It's just 25.9. That's around 26 microhenry. So you can change the parameters now. You can change the number of turns. You can change the wire diameter. You can change the inner radius of the helix, or you can even change the helical structure to spiral structure. But that doesn't make any difference that much because I know that it's quite pretty comparable and similar. But yeah, you can do a lot of things, and you can actually reach to that particular value by doing a number of hit and trials, I would say. And simulation is very handy with that because you can't do those things in real. So simulations come very handy, and they will help you a lot and save like tons of time. And it is a very easy task once you know, and once you get the hang of it, it's very easy. Yeah, that's it. Yeah, thanks for enjoying the tutorial. I guess I have helped a lot of people out there who were actually seeking for this particular tutorial. Thank you for that, bearing with me. Yeah, thanks, and do not forget to subscribe and put comments and suggestions down there. Follow the description, and whatever you like, you can, yeah, always ping me. You can send me emails. It's also in the description. And that's it. Give us a thumbs up and keep liking. Thank you.